We have these big fundamental challenges in physics. It's not that physics is wrapped up and done by any stretch. There's so much we don't understand.
What does a particle physicist do?
Particle physics is actually quite a big discipline, and there's lots of specialization. I mean, particle physics fundamentally is about what is the world, what is the universe made from. Most of the elements that we are made from ultimately have their origins inside stars. So that is true for, basically everything except helium in the universe was made inside stars of different types.
Physics gets very complicated also very quickly because there's a spectrum of things. Things can get too simplistic or get so complicated that you feel like it's not for me. Someone who's enthusiastic about science, what is your advice to how do you go about learning about it?
A lot of the time, the biggest breakthroughs in science come from these little weird observations in experiments or in astronomy that don't really make sense or don't fit with the current picture. And by really sort of studiously tracking down the sources of the anomalies, sometimes you get a really big breakthrough.
Harry, welcome to SparX.
Great to be with you.
Yeah, really looking forward to this conversation. I started reading your books just a few weeks ago, and it doesn't happen so often, with the science book that I was really not able to put it down. I started with the how to bake an apple pie from scratch, and then immediately jumped to space oddities. And I was going through those books, and later on in preparation for this, I was going through some of the videos that you've talked about your books. Kind of your joy for science comes across, those both through your book as well as through your presentations. It seems like you really like communicating about science, and like there's an infectious joy that come across, the way you communicate.
Well, thanks for saying that. I mean, yeah, I think the thing about science is that the reason I got into it is because I just love the sort of stories of scientific discovery that you kind of learn about when you're at school and then when you're at university. And I think that's sort of where the real excitement comes from. Science isn't this kind of body of knowledge as such. It's this process where you go from not understanding something to understanding something and seeing how that process happens, and also being part of it is really exciting. But also I think the reality of being a scientist, a lot of the time you're not thinking about, the origins of universes, these big cosmic questions. It's why will my piece of code not compile? And why does this graph look funny? Yeah. And so I think talking about the subject in a sort of bigger picture way reminds you, sometimes you can kind of get lost in the drudgery of every day, trying to get some paper out or analyze some piece of data. And it reminds you why you're doing it in the first place.
No, amazing. And I'm glad, you do what you do, like in addition to being a, very serious scientist by the day, but finding time to communicate in all these complex topics, in a way where people are able to relate to. I think I would like to believe I was able to follow along most of it. But let me just go back and first, just maybe a request to explain, what does a particle physicist do? It's for most of us from outside, and we all heard about, CERN and, discovery of Higgs boson in 2012 and so on. But what does day-to-day for a particle physicist look like?
I mean, it depends, because particle physics is actually quite a big discipline, and there's lots of specialization. I mean, particle physics fundamentally is about what is the world, what is the universe made from. We're trying to understand the basic stuff that we are made out of. What are the basic constituents? What are the forces? But there are lots of different types of way of approaching this problem. So you have, I suppose, at one end of the scale, theoretical, sort of really high-end theoretical physics, where you have people who are working on pen and paper and, writing down equations. That's a relatively small number of people. At the other end, you have experimental physicists who are, in a laboratory building some piece of equipment. And then there's a sort of spectrum in between the two. And I suppose I'm an experimental physicist, but my role is mostly in data analysis. So I work on a detector at CERN, on this machine called the Large Hadron Collider. It produces huge amounts of data, and my job is to use various techniques to sift through this massive data set and look for signs of new processes, new phenomena that we've not seen before that could help us address some of these bigger questions that we're trying to answer. But my day-to-day, I mean, it's quite varied because of, my role combines this kind of communication element. But in terms of the actual science, a lot of what I'm doing is sitting in front of a computer, writing computer code in Python or C++, using machine learning to extract patterns from data sets, writing papers, working with students, talking to them. So it's good. There's a lot of meetings at CERN. So you're in these big international collaborations. My experiment's got about 1,500 people So there's a lot of Zoom meetings, and we were doing a lot of Zoom meetings way before it was popular, going back, decades, because we've been spread, my colleagues are spread all over the world. I'm based in Cambridge, but, the experiments in Geneva, and then there's people all over the world who are working together.
So a lot of time it does look like a regular corporate job as well.
Yeah. It would look, I suppose it probably doesn't from the outside look very different to, say, someone working in data science or working in, finance, I guess, although less glamorous surroundings usually, because you're in some kind of 70s office in the university.
But part of, do you also kind of follow along what's happening in the research, like have to read, all the research papers, etc., as part of the job? Yeah,
so you go to conferences, going to workshops, hearing and what the latest developments are. Yeah, reading the sort of latest papers that have come out, keeping on top of what's going on. That's a big part of it as well, yeah.
Got it. So let's start with your, first book, How to Bake an Apple Pie from Scratch. And I know in some of your other talks, you go out of your way to explain that this is not about the actually baking an apple pie. But the premise of the book is, very ambitious. You're trying to explain pretty much every single ingredient that goes into building an apple pie. How do you build from scratch, starting with inventing a universe, which is probably too hard to explain even today. But just what was the thought process? What was your vision for the book? That to go after such a comprehensive topic to be able to explain every single element that has been created through various processes over the last 13.8 billion years.
Yeah, I think the story of the book is really the story that motivates me in my research, which is this attempt to understand the world around us, the stuff it's made from, and where it came from. So it's the story really of the origins of matter. So and its fundamental nature. How do we figure out what we're made from, and how far back through the history of the universe can we trace the ingredients, and will we ever understand the ultimate origins of everything? Essentially, that's so it's a huge story that's 13.8 billion years long. But what the approach, I think, when I was working with my my literary agent on this, was trying to find a way of hooking it to something more relatable. And there's this famous quote that kind of is quite well known in physics from Carl Sagan, who was an American popularizer of science and astrophysicist as well. And he had this series in the 80s called Cosmos, which is one of the first big budget television documentary series. And there's this very famous, quite famous scene in it where one of the episodes begins with an apple pie being made in some kitchen, but with this kind of very portentous soundtrack that's actually, I think it's the same composer as did the soundtrack for Blade Runner, so it's lots of 80s synth. And then this apple pie is brought out to Carl Sagan, who's sitting in this grand oak panel dining hall actually at Trinity College in Cambridge, and he looks at the camera with a little twinkle in his eye and says, "If you wish to make an apple pie from scratch, you must first invent the universe." And the idea is, even an object as mundane as an apple pie, if you really want to understand its ultimate origins, you have to go right back to the Big Bang to sort of figure that out. So this was a sort of hook that I returned to through the story to sort of say, well, we're starting with an apple pie and we're trying to figure out where it comes from. But really the story is about the origins of matter, the origins of the universe. And will we ever ultimately be able to say how it all began and where it all came from?
And before we go to the actual ingredients, the story of how different things came to be, you actually burnt quite a few real apple pie as well, right?
Yeah. I did this very silly experiment. So, like, my father, my dad, when he was a kid in the 60s, was a very keen amateur chemist. So in those days, like, there was no health and safety. So you could go to your local chemical supplier and buy more or less anything. And there was this whole community, I think, of small boys who would effectively make bombs in their back gardens. And
good old days,
yeah. So he has a lot of old chemical apparatus, like a Bunsen burner and a few other things. So I had this sort of thought, well, this slightly silly thought. If you were presented with an apple pie and, you were sort of told, asked, figure out what this is made from, what might you do as a scientist? So basically, we did this experiment where we shoved some apple pie in a test tube, we heated it up to a very high temperature, and we watched what happens. And you see it starts to break down into different substances, like this strange misty gas came off, then liquids come off, which you can collect, and then you end up with this black charred substance in the tube. And that's a sort of jumping off point to talk about, well, the black stuff, it's basically carbon. You've reduced the apple pie to a sort of lump of coal. And then there's all these other liquids, water, oxygen, other things that have evolved. And then you can sort of say, well, okay, we have these basic chemical elements, and we can start to ask, where did carbon come from? Where did oxygen come from? Where did the hydrogen come from? And so on.
All right, so where does all this stuff come from? Because for most of us, either comes from grocery store, you grow in the field, or you dig up a hole in the ground and dig, carbon out. But where does this really come from, and how do we know where does it come from?
Yeah, I mean, it sort of depends. But I mean, the first part of the story really is, okay, you have carbon, you have oxygen, you have hydrogen, you have all these other elements. And what are these things actually, deep down? And so the beginning of the story is really about the realization that the basic units of the universe are atoms. And it used to be thought that atoms, there's about 90 different chemical elements in the periodic table. Yeah. And the idea was there were 90 atoms, and they were all like unique Lego bricks, and they were fundamental, and you couldn't break them down. And if you asked a scientist, before the 19th century where they came from, they would say, oh, God made them at the beginning of time, and they've just been around forever. And at the start of the 20th century, scientists started to do experiments where they found they could break atoms apart, and you start to find these smaller particles that come out, electrons, protons, neutrons. And once you see that atoms are composed of these smaller things, you can sort of see, well, actually, okay, carbon is made up of, in some sense, is made up of hydrogen. And you could actually start to think, well, if these things are made of smaller things, maybe they were assembled somewhere. Yeah. And the question then is, well, how did these basic constituents come together to make all these different elements? Yeah. And this is a sort of big research project, I suppose, that spans decades during the 20th century. But the basic problem, if you want to, the hydrogen is the simplest atom. It's one proton, one electron going around it. So carbon, for example, has got 6 protons, 6 neutrons, 6 electrons. And the question is, how do these things coalesce? And when you want to make an atom, the big challenge you have is that if you start off with hydrogen, you want to make the next element, which is helium. You've got to force protons together. Yeah. And protons are positively charged, so they repel each other. And the closer they get together, the more they repel each other. So you have to get them going really quickly to overcome this repulsion so they can fuse. And the debate in the early 20th century was, well, where in the universe might this happen? Yeah. And there was an astronomer called Arthur Eddington who realized that one place in the universe where this might be possible was inside stars. And he had come up with the first theoretical model of the conditions inside a star, figured out that the temperatures there were in the millions or tens of millions of degrees. And at those temperatures, you could fuse hydrogen together to make helium. And so that is, most of the elements that we are made from ultimately have their origins inside stars. So that is true for, basically everything except helium in the universe was made inside stars of different types. So stars like our sun make most of the carbon in our bodies. Bigger stars that go supernova, these things that explode very violently, they make elements like oxygen and various other heavy elements. And then there's even more extreme objects like neutron star collisions, all kinds of crazy stuff that goes on at the sort of very extreme end. And through all these different processes, you populate the periodic table, and over billions of years, these objects have synthesized hydrogen into all the other elements that we see in the universe.
So if I understand this correctly, when you look up the, our sun, it's basically fusing hydrogen into helium, pretty much day and night for billions of years. Yeah. And the heavier elements is probably make it just towards the end of its life, which is probably, 5 billion years from now.
Yeah, that's right. So the sun is in its core fusing hydrogen to make helium. And in about 5 billion years, there's so much helium will accumulate in the core that the fusion will stop because there'll be no more hydrogen fuel. And when that happens, the core of the sun will start to shrink and heat up, because what stops the sun from collapsing under gravity is this internal heat source from the fusion, the nuclear fusion reactions that are going on. They keep it inflated. So when that switches off, the internal furnace goes off, it starts to collapse. Yeah. And as it collapses, it heats up. And then what happens is the sun, the temperatures get so high that it reignites fusion in a kind of shell surrounding the core. So you imagine all this heat coming out from the core. Fusion restarts, and then sun will expand to become what we call a red giant. Yeah. So it will swell in size many, many times, probably enveloping Earth, Mars, all the inner planets will be gone. They'll be inside the atmosphere of the sun.
5 billion years from now.
So as long we don't have to worry about it for a while. And then what then starts to happen is eventually the core gets so hot that helium atoms, nuclei, start to fuse to make carbon. So you're now starting to make carbon in the center of the sun. And after a while, the whole core of the sun gets turned into carbon and oxygen, and it loses its atmosphere. And a lot of these elements are then wafted out into space. So the sun will end up as this very small, hot, dense object called a white dwarf, which is the kind of exposed core, which is mostly made of carbon and oxygen. Yeah. And then it will send into a space its atmosphere of helium and bits of carbon and quite a lot of carbon. And that's where those sorts of objects gave rise to the carbon that we're made from. So we are made of bits of old, dead, sun-like stars that died, billions of years in the past in this way.
That is incredible. And all of this, we have we as in like larger scientific, community has figured out in last 100 years or so.
Yeah.
And today, these things are, when let's say somebody, is reading about it or listening on this podcast, how strong is evidence for all this? How well do we know that this is not a conjecture or a educated guess, but there is rock solid evidence that's exactly how things would have happened billions of years ago. For all these stars to die and make all this material in the process, throw out and let other stars and planetary system form and so on. Sounds pretty exotic.
Yeah, the evidence is really very good. So we know we have a very detailed story of most of the elements. Now, there are bits that we don't completely understand. There's some details that are still to be figured out. But broadly speaking, and you have evidence from two different places. There's basically two ways we have of understanding the universe. One is to look out into space. Yeah. The other is to do things on Earth in the laboratory. And both of these different ways give us information about what's happening inside stars or during their lifetime. So one of the ways that we know this is we can look at stars, and because there's a huge number of stars in the sky, we can see them at different points in their lifetimes. They're all different ages. And if you use this, there's this technique, probably the most important breakthrough in astronomy after the invention of the telescope was this development of something called spectroscopy, which is where you can break the light from a star or from the sun into a spectrum using a prism, where you get this rainbow spectrum. And if you look at the light in detail with a microscope, what you'll see is it's not a perfect rainbow. There are these like dark and light bands that appear. So bits of the spectrum that are missing, other bits that are brighter. And what these are the kind of unique fingerprints of different chemical elements. So each atom has a set of colors that it emits and absorbs. And that's essentially a quantum effect where electrons jump between different energy levels around the atom. And when they do that, they either absorb or emit certain colors of light. So by looking at, say, sunlight, if you break the sun's light into a spectrum, you can identify what elements are present in its atmosphere by looking at the spectrum of an atom in the laboratory. So you heat up some element, it will give off those colors. You go, okay, that's helium, that's oxygen, that's carbon. So we can look at all these stars in the night sky. We can look at dead star systems with these clouds of gas that have been emitted. We can see in those luminous clouds traces of all these elements. And that's how, from astronomy, we've pieced this together. In terms of what's going on inside the stars, now that you can't see so easily because it's inside the star, but in the laboratory you can recreate the conditions that exist inside stars by banging atoms together with accelerators or other things, and you can then test the reactions that we think are going on. And there's even ways of looking, you can actually now look inside the sun using particles called neutrinos, which are produced in the core in the nuclear reactions and actually escape straight out of the sun, and you can detect them on Earth. So we have all these different ways, essentially, of piecing together this story, and it's pretty solid. So we have a very good understanding, but it's still evolving. I mean, one of the really interesting things that happened in the last few years is it used to be thought that precious metals like gold, platinum, are made in supernovae. So these massive stellar explosions, incredibly violent, when a massive star dies and it blows up and briefly shines brighter than an entire galaxy. It was thought in the extreme conditions in these explosions, you make all the heavy elements. But actually, more recently, there was a discovery by an instrument in America called LIGO, which is a gravitational wave telescope. So it doesn't look at the universe in light. It looks at it in ripples in the fabric of space-time. And they detected this very violent collision between two objects called neutron stars, which are basically the dead husks of massive stars that have blown up. And you get these very, very heavy objects that are about the size of London, or city, a big city, so 30 kilometers or so across, but they weigh as much as the sun. So they're incredibly dense. And when they collide, they give off these gravitational waves, but they also create this incredibly violent explosion. And when astronomers looked at the light produced by this object, this collision, they saw huge quantities of gold, platinum being produced in this collision. And by some estimates, I think it was that this collision produced enough gold to make 30 solid gold planet Earths. Wow. So actually, if you have a piece of jewelry with any gold or platinum in it, what you have on your, what you're wearing is a basically a remnant of a massive collision between these two very extreme objects billions of years in the past. And so our understanding is still evolving, and there are still bits of the puzzle that we don't fully understand, but the overall picture is pretty well understood now.
Got it. So we use this, method of spectroscopy to look at light from distant stars, And is it only for stars which are nearby in our galaxy, or can we look at the spectroscopy of individual stars from, galaxies which are far away from, in other galaxies, maybe galaxies close by like Andromeda, or even galaxies which are, hundreds of millions of light years away?
Yeah, I mean, so, you can look at the spectrum. As long as there's enough light, you can look at a spectrum. Now, as you look further out, it's harder to resolve individual stars, obviously, because you get merged with the sort of overall, like, other stuff in the galaxy. But yeah, so you can sort of look out into the universe, and you can see that, all the galaxies are made of basically the same stuff. There's the same atoms everywhere. And you also can use these spectra that you get as a way of estimating things like the expansion rate of the universe. The universe is getting bigger.
Yeah.
And because of that, the light that's emitted by distant stars, as it travels through space is expanding. That light gets stretched. It's what we call redshift.
Yeah.
And so you can use this as a way, because say, transitions in, say, quantum jumps in hydrogen are the same everywhere in the universe.
Yeah.
There are certain colors. And what you see when you look very far away is those colors are shifted more towards the red. And you can use that as a way of working out, the rate of the universe's expansion. So it's not just about telling you what the universe is made from, it's also telling you about its evolution and how it's changing through history.
And how are we to visualize that? And how do we even know how far these things are? Because the numbers that we talk about, that truly astronomical. We talk about things being billions of light years away.
Yeah,
which is a humongous distance.
Yeah,
how do we know that?
It's a big problem. So one of the things about astronomy is it's very hard to know how far away an object is. Yeah. There's a famous scene in this. I don't know if your listeners will be familiar with Father Ted. Probably not. But there's a British sitcom which is about these Irish priests, and one of them is very silly and not very clever. And they're on a caravan holiday, and there's a scene where Ted, who's the slightly smarter one, is trying to explain to his colleague Dougal the concept of perspectives. They're sitting in a caravan. There's some cows out in a field, and Ted has this little model cow, and he's like, Dougal, this one is small, the ones out there are far away. And this is basically the problem we have in astronomy. When you look at a star, you don't know if it's a bright star that's far away or a dim star that's close. And there are lots of very clever ways of trying to piece together the distances you have in the universe. And there's this thing called the cosmic distance ladder, which is a series of clever techniques of kind of building basically a measuring stick out into the universe where you can figure out the distance to objects. But broadly, the way it's done is there's something called parallax, which is the effect that if you've ever sat on a train, say, and you see that things in the foreground move at different rates to things in the background, and you can use that effect to estimate distances geometrically. So when the Earth goes around the sun, what you can do is if you take a photograph of the sky 6 months apart, stars that are close enough will shift their position slightly relative to each other, relative to sort of further away stuff. And you can use that through basic high school geometry to work out the exact distance to that thing. But that only works for quite close stuff, because when it's very far away, the shift is so small, you can't perceive it anymore. So that works with stars like in our local galactic neighborhood, so in the Milky Way, in our general environment. The next technique was discovered by an American astronomer called Henrietta Swan Leavitt in the early 20th century, which is she was studying these stars called Cepheids, which are young, very hot stars they're unstable. They have these pulsating atmospheres, so they get bigger and smaller with a characteristic frequencies. They kind of pulsing like this. And she discovered there was a relationship between how quickly they pulse and how bright they are. So the slower they pulse, the brighter these stars are. So and this is a kind of linear relationship. So if you know that relationship, and then you see a Cepheid in a distant galaxy, and you can see its pulse rate, you can work out how bright it is. And if you know how bright it is, you know how far away it is, because you can tell how bright it appears from your telescope. So you have all these techniques that are kind of building on each other and allow you to extend to greater and greater distances. But it's a very difficult area of astronomy, and there's still arguments about, is it properly calibrated? Do we really know the distances? And quite a lot of big questions in astronomy hinge around, can we estimate distances properly? Because that relates to things like, how fast is the universe expanding? What's the sort of the cosmic history of the universe? Are there forms of matter or energy in the universe that we don't understand that are changing the expansion rate? So these sorts of questions are really fundamental to our understanding of the universe as a whole.
God, so today when we talk about distances, especially distances which are like way out there, we talk about, I think, from my understanding, we say like, the observable universe is something like 45 billion light years or so.
Yeah.
We take those distances for granted, or we have to take them with a pinch of salt and saying, look, all this stuff needs to be still figured out and need to be more accurate in future.
All of these in science, any quantity that you estimate or you measure comes with an uncertainty.
Mm-hmm.
So you have some expression of how well you think you know something, and so generally speaking, we will have I have to say I'm not a cosmologist or astronomer, but for the size of the observable universe, that number will come with some uncertainty. I don't know exactly what it is, but it's it's presumably quite small. I think it's quite a small fraction of the total number. So there's room at the edges for things to be a bit different. But the overall picture is pretty solid, I think.
Got it. So within a certain margin of error, we have reasonable good idea of how big at least the observable universe is.
Yeah.
Beyond that, I guess, very hard to speculate. Maybe I think maybe cosmology has something to say about it. But I want to go back to, the building apple pie from scratch. And so some of the stuff is, fused in stars. I guess original hydrogen was just created, in Big Bang, that's all the hydrogen that we see is probably been there, and probably helium as well. Any other, like as part of, the you go through the ingredients, any other exotic phenomenon which contributes to an eventual apple pie or anything else that we consume?
Yeah, I mean, so the main ones are sun-like stars, supernovae, neutron star collisions. There are a few others, but those are the big ones that do most of the work. But then this, actually, the interesting about this whole story is, in the 20th century, there was a big debate about the origins of the chemical elements, and there was a group of scientists led by George Gamow, who is a Soviet physicist, who were of the view that the Big Bang, the sort of fireball at the beginning of the universe, had forged all the chemical elements. And then on the other side, you had people like Fred Hoyle, who was a Yorkshireman from England, who really disliked the idea of the Big Bang, and he was trying to prove that all the elements were made in stars. So you had these two rival camps, and the fact is actually neither of them are completely right. So the elements, eventually was found that it's not possible to make all the heavy elements during the Big Bang. The conditions aren't right. But also on Hoyle's side of the argument, you can't explain the abundances of all of the elements just based on stars. There's this big mystery. If you look at the total composition of the universe, it's about 74% hydrogen, 25% helium, and about 1% everything else. So all the other elements, the stuff that make up the Earth and our bodies, are a tiny, tiny fraction. And the question is, if all of that stuff came from stars, why is there so much more helium than all the other elements? Because helium's the first step in a process that fuses everything else. And that was the sort of evidence, one of the pieces of evidence that the Big Bang happened. So to explain the huge amount of helium, you have to have this furnace at the beginning of the universe, very high temperatures in the first 15 minutes after the Big Bang, when hydrogen fused together to make helium. So most of the helium in the universe was made in the first few minutes of the universe, and everything else after that in the periodic table was made in stars. So actually this sort of stars versus Big Bang picture is sort of neither is right. You have to have both of them together to explain everything.
Guys, is today our understanding a majority of that helium is also from Big Bang?
Yes.
And if I'm not mistaken, I think Fred Hoyle actually, I think the whole name Big Bang is something, he was kind of mocking it or, didn't like it, and the name stuck.
Yeah, so Hoyle, he was a cosmologist, an astrophysicist, and he really disliked the Big Bang on a sort of philosophical grounds, I think. His view was that if you have a moment of beginning, that is inherently unknowable, and it kind of opens the door for, the role for God or creation or creator. So he was much more in favor of this theory called the steady state, which he was one of the architects of, because the origin of the Big Bang as a theory comes from this discovery by Hubble that the universe is expanding. So you see that you look into the distant parts of the universe, every galaxy at sufficiently large distances is moving away from us. And this leads to the realization that, okay, space is getting bigger. And if you wind the clock backwards, that means in the past it was smaller. And if you go far enough, everything ends up in the same place. That's sort of a basic idea. But Hoyle tried to sort of get around this by saying, yes, the universe is expanding, but it's always been expanding. And the reason it stays the same, it's steady, is because new matter appears out of nowhere, basically, in the vacuum and creates new stuff. So you can imagine these galaxies get further and further apart, but new atoms are coming into existence that fill in the gaps and make new galaxies. So the universe stays sort of the same, despite the fact it's always getting bigger. So he had, and actually, the piece of evidence that really clinched it for the Big Bang was the discovery of what we call the cosmic microwave background. So in the mid-1960s, two American radio astronomers detected this strange microwave noise that seems to come from the whole sky. And this was realized eventually to be the light left over from the fireball of the Big Bang itself that has been stretched from very bright visible light to this very faint, cold microwave signal. Yeah. And that was the thing that convinced most people that the Big Bang really did happen, because you could literally now map this radiation across the sky and you could effectively get a photograph of the fireball of the Big Bang. But Hoyle never even despite this evidence, he refused to accept the Big Bang until his death. So he carried on pushing the steady state theory. But most other cosmologists at that point.
And today now Big Bang, is a big part of, popular culture. Including the very popular, show that, a lot of people love. So, I mean, we have known about, I guess this, it's been about 60 years since, cosmic background microwave radiation was found. And now I guess it has been mapped to a very precise accuracy. And in some ways, I say, like, there's a picture of, pretty much Big Bang 380,000 years after the Big Bang. So very close up to the, beginning movements. And no one really doubts it now, right? The evidence is so strong that, this is our best possible knowledge of how the universe got created in the first place.
Yeah, I mean, you always find someone with a wacky theory that says, the Big Bang didn't happen. But yes, the vast majority of cosmologists are convinced. And that's, that comes from the cosmic microwave background itself. But another very strong piece of evidence for the Big Bang is the fact that it accurately predicts the abundances of the light elements that were fused. So, there's this theory called Big Bang nucleosynthesis, which means the synthesis of nuclei, making nuclei. And so there's lots of different bits of evidence that come together to sort of show this is convincing: the expansion of the universe, the cosmic microwave background, the abundances of the different elements. It all lines up. So, there is still room for modifications of the overall history of the universe. Exactly what kinds of matter and energy existed in the early universe and how have they evolved through cosmic history. So that is still up for grabs to a certain extent. But in terms of the big story of the Big Bang, it happened, the evidence is pretty overwhelming.
It's incredible that, just, in barely 100 years or so, I guess, history of science is probably longer, but, most of what we know about how the universe works and how it's created in the last 100 years or so, and it's a fascinating story, as, great to read about a lot of details in your book. One of the ingredients in which probably doesn't directly go into making an apple pie, but you do talk about, this whole idea of antimatter, which people were, from what I understand, not really looking for it, but at some point, I think, it was conjectured and eventually was found. And today we have, we are able to produce antimatter in lab and study it. That sounds, absolutely fascinating.
Yeah. I mean, antimatter is one of those amazing stories in the history of science, in that it was not something that anyone had really imagined before. And it came out of essentially the combination of two of the big ideas that had shaken physics in the early 20th century. So on one hand, you have quantum mechanics, which is the new framework for understanding the atomic and subatomic worlds that emerged in the early 20th century. And then you have Einstein's theory of special relativity, which describes the physics of things moving close to the speed of light. And in the 1920s, physicists were trying to combine these two theories to understand atoms and electrons and things better. And there was a physicist called Paul Dirac, who was a Cambridge young theoretical physicist, who was the first person really to come up with what we call a quantum and relativistic understanding of the electron. And he came up with this equation, this very beautiful equation, that accurately matched all the experimental data in terms of how atoms behave and their spectra and electrons and so on. But it had this weird prediction that it predicted these positively charged electrons that no one had ever seen such a thing before. Dirac spent a lot of time trying to get rid of these positively charged electrons from his equations, but they seem to be a kind of unavoidable consequence of bringing quantum theory and relativity together. And eventually he was forced to conclude, on the basis of these theoretical principles, there must exist a kind of mirror image of the electron that is the same but has the opposite electric charge.
Right.
And then about a year after he made this statement, this positively charged electron was discovered by an American physicist in California using something called a cloud chamber. He saw this trail going through his instrument, going in the wrong direction, basically, for an electron. It was curving in the opposite direction. So this is the discovery of what we call antimatter. So this is a particle that's sometimes called the anti-electron or the positron. And we now know that for every matter particle, that in the universe, there is a corresponding antiparticle, which is exactly the same, but has the opposite charge. And there is this kind of actually, it raises some big questions because, well, the first thing that the discovery of antimatter does in some ways is it allows us to make matter for the first time, because it had been thought until this point that matter was indestructible. But actually with antimatter, you have this phenomena where you can put enough energy into a system, you can create out of the vacuum basically a particle and its antiparticle. They always come together in sort of mirror images. If you create particle, you create the antiparticle.
And this is not science fiction. We can do this in lab today.
Yeah, we do it routinely in the laboratory all the time now. And if you bring matter and antimatter together, they equally will annihilate each other. So if you met a version of yourself made of antimatter, you would look exactly the same. You wouldn't be able to tell. But if you shook hands, you would explode. Sorry, microphone. You would explode in this very violent release of energy. So this gives us actually a mechanism in the early universe to produce matter from energy. So in the Big Bang, we have lots of energy, very high densities and temperatures. Matter and antimatter are being created all the time in this kind of fireball, the first millionth of a second, basically, after the Big Bang. But it also raises a big question, which is there is this perfect symmetry between these two forms of matter, where you create matter, you also create antimatter. So the question then is, why is the universe only made of matter? Why, actually more fundamentally, why is there matter in the universe at all? Because according to our current theories, what should have happened during the Big Bang is you get lots of matter and antimatter created. As the universe expands, cools down, there's no longer enough heat to keep making more matter and antimatter. And what happens is they all meet up and annihilate each other. And you end up with a universe that's empty. And so the fact that there's stuff in the universe and that we exist is a big mystery, and we don't understand how this happened.
We don't have any plausible explanation for why we see so much matter around us, but basically there is no antimatter.
Well, we have explanations. There are various theoretical ideas about how this could have happened, but at present we have no experimental evidence for these ideas, so they're sort of speculative at this point. So there are ways that you can do this theoretically. The challenge is how you prove one or other of these ideas to be true, because generally you need energies if you want to do this in the laboratory, you need energies that are enormous, and in some cases are unachievable with current or even future technology. So it's an open question at the moment.
Right. And going back to the 20s and 30s, when people started finding positron and other particles, and then there was a 20-30 year period where these particles were just showing up pretty much nearly every day. I think probably somebody remarked who ordered that, because there's this weird particle showing up that no one's even looking for or wanted, and just having to revise all the theories, which culminated into standard model. And then, at some level, physicists thought we are done. We've got a model. It works really well. It has huge practical applications. But there were some gaps around that, right? Which is, I guess, last 50-60 years, some of the work you do at CERN is related to kind of closing those gaps and things we think, where standard model might be incomplete.
Well, I mean, I'd say it's more than gaps. I mean, so I should say what the standard model is, but the standard model is a rather boring name for what I think is one of the greatest intellectual achievements of human beings. It's this theory of the basic constituents of the universe, and it's amazingly successful. It describes the matter particles that we're made of. So there are 12 matter particles in the standard model, and then there are 3 forces, electromagnetic, strong and weak forces. And this theory describes pretty much every experiment we've ever done with dazzling accuracy. So in some sense, we know it's a correct theory of the universe, but it's not so much that it has gaps, but it has yawning chasms in it. That from astronomy, we know that 95% of the universe is invisible. It's made of these substances called dark matter and dark energy, and we have absolutely no idea we have ideas, but we don't have any evidence for what these things actually are. And the standard model cannot explain them. So the standard model describes the 5% visible universe, the atomic universe that we're made from stars and planets and so on. But it has nothing to say about the 95% of the universe that's out there that we don't yet understand. So that is one reason alone for thinking there must be. The standard model is probably the edge of some bigger, more complete theory that describes these other phenomena. I mean, we also talked just now about antimatter. The standard model predicts the universe should not exist. It predicts that antimatter and matter should have annihilated each other at the Big Bang. And any theory that predicts its own authors don't exist is in trouble. So there's clearly phenomena that we have yet to discover that will expand this theory to something larger. And that's, broadly the goal of particle physics in general, is we're trying to find the places where in the laboratory, the standard model breaks down. So we have all this evidence from the universe, from astronomy, but what we don't yet have is a fundamental understanding of how to answer these questions. And that's why we do experiments at the Large Hadron Collider and at many other places around the world to try and get some clues so we can answer these questions.
And in what ways, the experiments at CERN and what we have, I think, LHC is probably in operation for now 10, 12 years or a little more, I guess. In what ways LHC is helping, move our understanding forward? What do we know today that maybe we didn't know 15 years ago?
I suppose there are two really big things the LHC has done. The first is it discovered a particle called the Higgs boson, which you may have heard of, which was the last particle predicted by the standard model, which hadn't been found. And the Higgs is really, it's not just another particle. It has this very central role in our understanding of physics. I mean, it famously is known in some circles in popular culture as the God particle, which I have to say I don't like the name. But the reason it was given that title is because it has this crucial position in that the Higgs boson is connected to the reason that the particles that we know have, the fundamental particles we're made of have mass.
Yeah.
And it also is responsible for giving form to the various forces that are in or some of the forces in the standard model. So it has this kind of almost role as a conductor of the standard model. But there are also things about the Higgs boson that are very strange, that are very mysterious, which are connected to why the universe exists in the form that it does. So there are lots of mysteries around the Higgs boson that we don't yet understand. We know it now exists, but exactly what this thing is and what role it plays in the universe, and it may have played in the early history of the universe, we don't yet understand. So the LHC has sort of opened, I suppose, a new research area, which is the study of the Higgs boson. And that is going to be one of the great projects of fundamental physics in the next half century, is to actually zoom in on this thing and figure out what it actually really is. Like, is it actually a fundamental particle? Is it maybe something that's made of other constituents? And what role did it play in the formation of the universe in the very earliest moments of the Big Bang? So that's one element of what the LHC has done. The other element, I think, is it's essentially torn down many of the really popular theoretical explanations for some of these big mysteries that we face. So if you went back 15 years to before the LHC, there were particular theories that were very popular. There was something called supersymmetry, which is this big theoretical paradigm that claims to do many things at once. It explains, for one, what dark matter is. It helps to unify the various forces in the standard model to a sort of more, elegant, simple structure. It also addresses some very strange issues around the Higgs boson. So it did many things at once. And it was regarded as a very promising avenue for exploration. And the hope was, when the LHC switched on, we would discover what we call superparticles, sparticles, these particles predicted by supersymmetry. Now, we haven't seen any evidence of them. So supersymmetry as a theory, it has really, what the LHC has told us is that at least in its most basic forms, it's not an accurate description of the universe. And there are various other ideas to do with there being more dimensions of space than we perceive that were being tested at the LHC. So the LHC, in some sense, it's sort of like been a bonfire of theories. It's destroyed all these ideas that we thought were very promising. And it's left physics in a very different place, where we still have these big mysteries, but we don't have yet a evidence for how to solve them, or a lot of the good, more promising theoretical ideas have gone by the wayside. So, I think that one definition of a successful experiment is one that leaves the field looking different after you've done it. And this is definitely true of the LHC. Now, it may not have changed the field in the way we might have hoped. It would have been great had we discovered new particles that would help us address these mysteries, but it's certainly taught us a lot. And that's probably the other big impact. The question now is, the LHC is still going to run for another 15 years or more. That's about 15 years or so. And the question is, will we see new particles, new phenomena in that time, or will we, at the end of that process, still have the standard model and no explanation for these big mysteries that we're getting from other places in the universe?
Right. I'll come back to the future of LHC and on even maybe the mechanics of how these particle colliders work. But since we're talking about Higgs boson, Harry, this reminded me of, I think, from what I understand, boson particles are named after Indian physicist Chandrasekhar Bose. And we have a very peculiar history of physics in India. There is not a whole lot of research, but there are some of these guys, Chandrasekhar Bose being one, C.V. Raman another one, I think they call Raman scattering is named after him. just come out of blue. They are, working in these obscure universities, and then suddenly, they are able to make massive contribution. And I think from what I understand, bosons are a family of particles which pretty much are involved in all fundamental forces of nature.
Yeah, that's
so
right.
Must have been a pretty significant contribution by Chandrasekhar Bose, I think, in probably 50s, 60s. I think he collaborated with Einstein also at some point.
That's right, yeah.
How much, background you know.
Yeah, so I mean, basically in quantum mechanics, particles fall into one of two camps. So you have fermions on the one hand, and fermions are matter particles. So things like an electron, quarks are fermions. They're named after Enrico Fermi, the Italian physicist. And then on the other hand, you have bosons. And bosons, as you say, the sort of theory behind them came from Chandrasekhar Bose. And the thing that determines the difference between these two things is something called spin. So particles possess this property, which is a bit like they are little spinning balls. Now, they're not. But it possess this, what we call intrinsic angular momentum. Angular momentum is this kind of rotational form of momentum. So a ball that's spinning like a rugby ball going through the air, that has angular momentum as it rotates on its axis. So particles possess angular momentum. And in quantum mechanics, angular momentum it comes in these discrete lumps, quantized lumps of size 1/2. It doesn't really matter what the half is of, but it's this basic unit. And fermions, matter particles, have spin 1/2 or 3 halves or 5 halves or so on and so on. And bosons have integer spin, so spin 0, 1, 2, 3, 4. And whether you have half integer spin or integer spin completely changes how the particles behave. So it's to do with the statistics, I suppose, of quantum mechanics, that there is this rule that applies to fermions called the Pauli exclusion principle, which says that no two identical fermions, so spin half particles, can be in the same quantum state. So that means that in an atom, you can't have two electrons in the same energy level with the same spin going around, say, a hydrogen or a helium atom, for example. And this fact is really important because if it were not true, matter would collapse. So the thing that gives us means we take up space and you can't walk through walls and matter is solid is basically a quantum mechanical effect that prevents everything from ending up in the same place. But bosons, on the other hand, are very different. So bosons can all exist because they have integer spin. The way this kind of essentially sets the rules of their behavior in the quantum world means that they actually can all exist in the same quantum state, and in some sense prefer to all be in the same quantum state. So a laser beam, for example, is what we call a coherent quantum state of photons. Photons are also bosons. They're spin 1. And you can get a laser is basically when you have a load of photons all, in sync with each other, and you get this, very, this coherent form of light. You can do all kinds of cool things with it. You also have these properties with very low temperature, say helium, which becomes what we call a Bose-Einstein condensate, where you have these particles all end up in a single quantum state, and they have all kinds of strange properties. So so actually, what dictates the difference between matter and what we call matter and what we call forces? Forces are all communicated by bosons, so photons, gluons, maybe gravitons, other W's and Z bosons. So these are all particles that have integer spin, and then Higgs, which is unique in that it's the only spin 0 particle. So it's a boson, but it has no spin. It's 0. And that gives it lots of strange, unusual properties that make it very different from, say, the forces. So, it's a really fundamental aspect of physics and a very important contribution to understanding.
And I'm glad, we have that level of understanding. Because I think butchered his name is S.N. Bose. Chandrasekhar is another guy of
you're right,
So let's come back to CERN. And this is a 27-kilometer long collider. Can you just explain to our audience that why is it that long? Why do we need to accelerate these particles and keep, colliding them? How does it help us understand, fundamental ingredients of nature better?
Yeah. I mean, what the LHC and all colliders are, in some sense, is they are matter-making machines. So the reason you accelerate particles to very high energies is when they're going very, very fast, they have lots of kinetic energy. And when they collide, that kinetic energy gets converted into forms of matter that often haven't existed in the universe since the very earliest moments of the Big Bang. And generally speaking, when we are looking for new particles, we're looking for particles that have very large masses compared to the stuff that we're made from. So, for example, the Higgs boson has a mass that is over 125 times larger than the mass of the proton, which is one of the basic constituents of atoms. So the only way you can make a Higgs boson is if you put enough energy into the collision that you can create one of these things, basically. So that's why you need to accelerate and go to high energy. And the higher the energy you can reach, the heavier the particles you can make. So let's imagine, for example, that there's a dark matter particle. We think there is a dark matter particle out there. That may have a very large mass. So the bigger the higher energy you get to, the more chance you have of discovering it. It's like exploring a kind of landscape, and with a more and more powerful sort of instrument. Now, why are these things so big? The basic answer is that you have to, in order to accelerate these things, there's broadly two ways of doing acceleration. You can either accelerate things in a straight line. So you have like a kind of a gun, essentially, that fires particles in opposite directions, they collide. If you want to do that, you have to accelerate them up to very high energies in one go. And that means you have to have lots of accelerating elements. The way you do that is with usually very high voltages. So you're passing these particles through very high voltages that get accelerated. And the longer you make your machine, the higher the voltage you can get them to, and the higher the energy. So the bigger. With the LHC, it's a ring-shaped machine. So this gets around the problem. You don't have to. The reason you have a ring is you can send the particles around, and every time they orbit the machine, there's a little bit of it, which is only about 30 meters long, that gives them a kick. So they kind of get a kick every time they go around the ring, and they get higher and higher and higher in energy that way. So that's why you have a ring. Now, why is the ring so big? Well, when these protons are going at full speed, which is about 99.999999% the speed of light, they're going very fast. In order to make them curve in a ring, you have to apply force to pull them towards the center of the ring. And at those speeds, you need a tremendously strong force to get them to bend. It's a bit like, if you're driving a car around a corner very fast, you need to have a lot of traction in your tires, otherwise you'll slide off the road. And the limiting factor, so the bigger the machine is, the more gentle the curve is, and the less force you need to pull it in. On the other hand, if you have a stronger force, you can make it smaller. So the thing that kind of that limits the size of the machine is how powerful a magnet can you make. So what we use to bend these particles around are these very powerful superconducting magnets. So, if we could make magnets that were 10 times stronger, we could make a machine that was 10 times smaller, more or less. But so it's a trade-off basically between how big a ring can you afford to build and how powerful can you make the magnets. And the LHC, when it was being developed and thought about in the 90s, which was when it was sort of seriously being worked on, they were sort of planning for a machine based on magnet technology that did not exist. They knew they were going to have to develop 8 Tesla, very powerful superconducting magnets, and that was part of the R&D. So it's sort of, it's a trade-off really between, can I afford to dig a massive tunnel, the civil engineering and all of that, and also the equipment, and then, how powerful can my magnets be?
And today, I guess in LHC, we are able to accelerate protons to a certain speed. For future research, do you think we need to go to much higher speed, which will require different type of colliders or different way of doing things, or the current energy is sufficient to figure out, everything that we don't know today?
I mean, it's probably the case that the LHC is not energetic enough, powerful enough to answer all these questions. I mean, with the LHC, still got a long way to go. So we may discover things in the next decade that will help us start to answer these questions. But one thing we really want to do in the next phase after the LHC is to study the Higgs boson in real detail. And for the LHC is not an ideal environment for studying Higgs bosons. And the reason for that is that when you collide protons with each other, protons are not fundamental particles. They're made of quarks. So they're these things inside them called quarks and gluons that hold the quarks together. So when you fire 2 protons at each other, they're kind of like firing 2 haphazard bags of junk at each other. So the collisions are very messy. You might create a Higgs boson, but there's also a load of other stuff that just comes out from the proton-proton collision, and you have to sort of extract your signal from all this noise that's a mess in the detector. There's another type of machine which, instead of colliding protons, collides electrons and positrons, so electrons and anti-electrons. And when an electron and positron meet, they're fundamental particles and they annihilate. And then all you have is the thing that you are interested in making. So you have a very clean environment in your detector. So that's a great way, if you want to study the Higgs in precision and zoom in on it in detail, the idea is you build an electron-positron machine that runs at a certain energy that's the right energy to make lots and lots of Higgs bosons. So you make millions of Higgs bosons in a very clean environment, and then you can study them very pristinely and get lots of information. So the most likely next step after the LHC will be for a very large electron-positron collider. And the question is, which one gets built? Because there are different proposals. You have proposals for ring-shaped machines like the LHC, but these will actually be lower energy than the LHC. But there's an extra challenge with electrons and positrons, which is when you accelerate them in a circle, they radiate X-rays very powerfully, and the faster you accelerate them, the more they radiate. So basically, they scream away their energy. So if you try and get them going very quick in a ring, they like blasting X-rays out all the time. So you have to keep pumping more and more and more energy into the ring to get them up to high speeds. So you have to make the ring really big to stop the curvature from being too tight. So they don't. The tighter they bend, the more they give off this radiation. It's called synchrotron radiation, technically. So a ring-shaped machine that would do this would have to be about 90 kilometers, so 3 times longer than the LHC. There are other ways of doing it where you use a linear machine, where you fire electrons and positrons down a straight line. They, again, would be sort of, you can get to reasonable energy with sort of a 30-kilometer scale machine. But the disadvantage of a linear machine is that you can't get as intense collisions. You get fewer collisions because you only have one shot. You basically send these things, they go through each other, that's it. Whereas a ring, you can keep colliding the beams over and over and over again, basically. So there's a debate going on in physics at the moment about, what is the next machine? Can we afford it? Where's it going to be in the world? Is it going to be in China? Is it going to be Europe? Is it going to be America, Japan? And so the question really is, I think we're all agreed on what the kind of broadly, what's the physics we want to do. But the question is, what's the right machine to do it? And can it be built? And who's going to build it?
Got it. And is going to be some kind of bottleneck for, unless these machines are built over next, few decades, at some point we are going to kind of plateau and will not be able to move forward unless to be able to do future experiments and probe at energies which are today, not accessible to us.
Yeah, I mean, I think if collider experiments are the best way we have of studying the universe at small distances. So yes, I think if we don't get one of these machines, it will mean particle physics will be hobbled. There are other ways of getting information about the high energy regime. So you can directly produce new particles in a collider. There are also other ways of doing things where you make low energy measurements, where you're sensitive to very high energy scales through quantum mechanics. So basically you have these effects where a very heavy particle can actually influence things at low energy. And so if you make a very precise measurement of some low energy process, you can get little clues to what might be going on without having to build a big collider. So, an example of this in the first book, actually, there's a really cool experiment in Imperial College in London where they measure the shape of the electron, which is a bit of a weird idea, but electron's a tiny fundamental particle, but the shape of the electron really means how is its electric charge distributed? Is it spherical or is it like cigar shaped? Is it more squashed? And the shape of the electron turns out to be very sensitive to the existence of particles that may be very high in energy that we've not seen. Basically, in the vacuum, you have these virtual particles that are being created all the time, and they can modify the shape of the electron. So you have an experiment in the basement of a lab in the centre of London, not very big, size of this room, where you can probe the same energy scales indirectly that you probe at the Large Hadron Collider. So there are other ways of getting information, but they tend to be more limited. If you want, it's the analogy I often use is, it's like you're in a jungle and you're trying to find an animal, and some rare new animal, and the jungle could be very, very big and dark and dense and hard to get through. And so, a collider is a bit like you're going through the undergrowth and you're looking to kind of stumble upon the animal in some clearing. And if the jungle is very big and very dark and dense, that might be very difficult. The other way you can do it is you can, rather than try and find the animal directly, you can look for evidence on the forest floor. So footprints, broken branches here and there, droppings. And from all this indirect evidence, you can start to build a picture of what this animal might look like. But you don't get the same level of detail, obviously, as finding the actual animal. And so these are two different ways of the same thing. But usually these indirect and direct approaches work in kind of in tandem with each other. And often in particle physics, we've got indirect evidence for some new particle before we discover it directly at a collider. So you need both of these tracks. But if we don't get, I think, if there isn't a future collider built, it will mean that some of these big fundamental questions will remain out of reach. And it may be that actually what needs to happen is, these machines keep getting bigger and bigger. And that's because although we are innovating in how we accelerate and how we build colliders, it's kind of incremental. And maybe what we need is a revolutionary step where there's a completely new way of accelerating that gets you, to high energies on much shorter distances, and the machines become more affordable. And there's various technologies that are being investigated at the moment, but they're much more speculative and much more uncertain. So you have you can either go for the sort of tried and tested approach, which you'll be able to build it, but it will be very big and expensive, or do you take a more high risk approach where you spend a lot of R&D trying to build some clever new way of accelerating, but that may not pay off. So yeah, it's a tricky problem.
Got it. As a science enthusiast, I can only hope that there will be enough funding and recognition. And for listeners, people listening to this podcast, this is not, at one hand, we have this intellectual curiosity. We want to understand where does all this stuff come from, what are the underlying principles, but massive practical application now. They happen, sometime decades down the line. I mean, everything from transistors, computers won't, exist without that, or lasers, or GPS, or, there's so many things which have come out of, this, the advances that physics have made last, 100 years or so. Now it just may not be immediate, but there is a multiple reasons to, both to kind of move things forward as well as to understand where we come from. So Harry, I think, towards the end of your first book, the Apple Pie book, as well as I think most of the second book, Space Oddities, you talk about these anomalies. These are, strange observations which does not fit the current understanding. And you kind of, project them in some ways. That's very exciting because it points a way to possible, new theories, new explanation of the... So let's talk about some of these, maybe starting with this thing known as Hubble tension. This seems like, that whole interest and controversy around that is growing last decade or so.
Yeah. I mean, maybe it's worth saying something first about anomalies in general, because, I think there's this sort of caricature of how science happens, which is often that it's, some lone theoretical genius like Archimedes jumping out of the bath and shouting Eureka, or Einstein devising relativity in the patent office. But a lot of the time, the biggest breakthroughs in science come from these little weird observations in experiments or in astronomy that don't really make sense or don't fit with the current picture. And by, really sort of studiously tracking down the sources of the anomalies, sometimes you get a really big breakthrough. And the foundations of both particle physics and cosmology both lie in these sorts of small effects. So the Hubble tension is an anomaly that is, is dominating cosmology at the moment. And it's basically a disagreement about how fast the universe is expanding. And there are two different methods that are used, broadly speaking, to determine the rate that space is expanding. And there's what we call a sort of direct or local approach, which is where you look out into the universe, you look at galaxies, distant galaxies, you measure their distances, you measure their speeds, and you measure from those two things the expansion rate. So, how does the speed of recession vary with distance? And that gives you a number called the Hubble constant, which relates how far away a galaxy is to how fast it's moving. So that's the sort of direct method, and that uses some of these distance ladder approaches that I discussed, parallax, Cepheid star, these pulsating stars, supernovae, other things. So that's one way of doing it. The other way of doing it is you look at the light from the Big Bang, so the cosmic microwave background. So you look right back to the very early universe, and from the patterns in the cosmic microwave background, you have these temperature fluctuations that are like, if you look at the cosmic microwave background, it's not smooth. It's sort of this dappled sort of surface with little hot spots and cold spots. And by analyzing these temperature fluctuations, you can infer the properties of the early universe. So what existed in the plasma, the hot fireball of the Big Bang, how much matter, how much dark energy, all these sorts of things. And when you know that, you can then extrapolate from the cosmic microwave background using our standard cosmological theory to the present day. And you can predict effectively the expansion rate of the universe. So you have an observation based on what we see in the sky, and then we have this prediction tethered to the early universe. And when you look at these two measures of the expansion rate, they don't agree with each other, and they don't agree by quite a large amount. And depending on which measurements you pick, this is what we now call over 5 sigma, which means that these things disagree by more than 5 times their uncertainties. And when you get to 5 sigma, it's this slightly arbitrary thing in physics, but you tend to say that is a discovery of something. Now, the question is what? So why do these things disagree? And, there are a few different explanations. The most exciting explanation is that the theory that we're using to bridge the early universe to the current universe is missing something. So it's telling us there's something in our theoretical understanding of the universe that we don't get. So it could be that there is, for example, a new form of dark energy in the universe that varies with time. and has changed through the cosmic history. It could be that dark matter actually, rather than just being a one particle floating about in space doing nothing, it actually interacts and has its own set of forces. It could even be that our theory of gravity needs modification. So there are lots of big fundamental, like exciting explanations that would change our understanding of the universe and its history. But there's also the more prosaic, more boring explanations, I suppose, which is there is a mistake in one or other of the methods that's being used to estimate the expansion rate. And the real sort of focus of this has been on this distance ladder. So how fast the universe is expanding depends, how fast you measure depends on how far away things are. Yeah. And if you get that wrong, then you can see an anomaly that isn't really there, and it's really down to miscalibrating distances. And that's where the debate really is. It's like, is this a genuine effect? Is it a mistake in our distance estimates? And there are sort of, some leading figures that are in quite strong disagreement with each other. So there's a guy called Adam Rees, who is a Nobel Prize winning astronomer, won the Nobel Prize, or shared the Nobel Prize for the discovery of the accelerating universe, the fact the universe is expanding at an accelerating rate back in the late 90s. And this is the evidence for what we call dark energy now. And then you have, on the other side of the argument, one of the people on the other side of the argument is a very eminent astronomer called Wendy Friedman, who made one of the first really precise measurements of the expansion rate using the Hubble Space Telescope in the 90s. So you have these two titanic figures. And Wendy Friedman, I think it's fair to say, is much more skeptical about the Hubble tension. She thinks it's down to our ability to estimate distances, and her particular concern are these pulsating Cepheid stars that we use to estimate distances. She thinks there may be problems with the way it's being done. And she has her own set of measurements using different techniques that agree better with the theory. They don't agree perfectly, but they agree better. Adam Rees, on the other hand, is pretty well convinced that this is, and he's the one that's produced the most accurate measurements that are in tension with the prediction. And he's very much of the view this is a real effect. And
one of the arguments you make in the book is these kind of anomalies are overall good for science.
Yes.
It brings more attention. It probably, young physicists who are starting to, they will say, okay, this problem is interesting, probably worth my time. These doyens of astronomy, kind of fighting it out publicly or debating.
Yes.
It's overall, great. And I think another thing you talk about in the book is, in some way, some of these anomalies are growing. There are at least 5 that you talk about in your book, which is hopefully, means that, coming decades could be very exciting for physics.
Yeah. I think with anomalies, the thing you have to bear in mind is that if you have 100 anomalies, 99% of them go away at some point. So they turn out to be a statistical fluke, or they turn out to be some mistake in the experiment. 1 in 100 maybe tells you something fundamentally new about the universe. So they're a kind of dangerous and exciting area in the sense that they can lead you down a blind alley in some ways. But, even when anomalies turn out to be down to experimental mistakes, you always learn something. So, take the Hubble tension. It may be that the Hubble tension is telling us something profound about the universe and its history, and there's going to be something new that will emerge fundamentally from that anomaly. But if it is, as Wendy Friedman says, down to a limited ability to estimate distances, that is really important, because if we then, as a result of this, have a better understanding of how to measure distances in the universe, that makes our ability to study cosmology much more solid. And so we'll have a knock-on effect on future research. So these anomalies are sort of, they're both potential avenues for discovery, but they're also a way of sharpening your scientific tools. And even when they go wrong, where they turn out to not be something new, you usually improve your techniques and your methods, and you have a better understanding of how to do experiments and make observations that lay the foundations for the next step in exploration.
Right. And one fascinating anomaly you talk about, these strange, radiation coming out of Antarctica. I think, the much higher energy than anything that we have ever seen.
Yeah.
And without any plausible explanation for what might be causing these.
Yeah. So this is a really just kind of cool anomaly from the point of view of the experiment itself. So this was an anomaly seen in about 10 years ago now, by a balloon-borne experiment above Antarctica. So it's an experiment called ANITA. Basically what it is this big radio antenna that gets lofted into the Antarctic stratosphere on a NASA helium balloon. So this balloon goes up into the stratosphere, it swells to the size of a football stadium. It's this massive, imagine this massive translucent orb with this little antenna hanging about the bottom of it, and it goes around the continent on the circumpolar winds, so it circles the continent. And what it's looking for are radio bursts coming out of the Antarctic ice. So the experiment is designed actually to look for very, very high energy neutrinos coming from very violent objects in the distant universe. So it's a way of studying things like supernovae or supermassive black holes at the center of galaxies that spit out very energetic particles. They come in, they hit the ice, and they give off these radio pulses, and you can use that to do essentially very high energy astronomy. But what they saw a couple of times during the various flights of this instrument were very high energy cosmic rays coming out of the ice. So coming up from below rather than coming down from space. And that is really weird because there are no particles that would be able to travel through the Earth with such high energies. Because at very high energies, the interaction rate of a particle with atoms becomes very high. Even a neutrino, which normally neutrinos can just go through entire planets without ever bumping into an atom. But high energy, very high energy neutrinos, they will actually get blocked by the Earth. So the question is, like, what were these two things that we saw? And the exciting explanation is it's some new type of particle that could be related to dark matter, perhaps, that has come up through the Earth and given off this like radio burst. Or it could be that the more prosaic explanation is that it's actually the way you tell whether a particle's come from above or below is from the essentially the phase of the radio pulse. So is it kind of, does it go up then down, or does it go down then up? Does it sort of mirror? And if it's reflected off the ice, if it's come down and reflected off, it has one phase, and if it's come up from below, it has a different one. Now, these signals looked like they are unreflected.
I see.
But one proposition is, well, maybe their radio waves have bounced around inside the ice in a complicated way that makes them look as if they are coming from below, but actually they're reflected. So, and that could be because there are weird subglacial features in the Antarctic ice sheet that we don't understand, subglacial lakes or compacted layers of ice or snow or whatever. So, again, you have this like thing, you might learn something about glaciology or you might learn something about dark matter. And it's another example of one of these things that we don't really yet understand what's going on.
So if you're lucky in coming years, or maybe it may take decades, we'll know exactly, it may be something super interesting, or it may be something, some straightforward explanation. Again, another area I think you talk about, which has to be, eventually when we find explanation, has to be super interesting, which is, I guess, both the nature of dark matter and dark energy. I think you talk about some of these experiments being done. I've been trying, I think it's been 30, 40 years that we have conclusively know that there is something, this halo of non-interacting mass, which is all around us. But beyond that, we really don't know what it is. But there are very serious experiments being done. And are you optimistic about, we'll find something in next 10, 20 years to be able to explain?
It's so hard to say. I think you have to be optimistic because otherwise you give up. But I think, what has turned out to be the case, it's very hard to make these discoveries. And we've looked for dark matter, say, in lots of different ways, at colliders like the LHC, in direct detection experiments where you have a big tank underground and usually in a mine shaft with very cold gases, liquid gases, and you wait for a dark matter particle from the outside universe to bump into your detector and give off some signal. And, people have built more and more and more sensitive experiments and still no sign of dark matter. So, this is leading people to kind of revise their ideas about what dark matter might be, what kind of particle is it? Is it something else? Do we need to do different sorts of experiments? But that's the way, you're doing this very broad search. And the broader it is, the better the chance that you'll find the thing that is actually causing this effect. So the prize is huge because if you see this, if you get a clue to what dark matter is, you've opened up a window on this, huge section of the universe that until now we've had very little information about. So I think you have to be optimistic. But as I answer whether we will see anything in the next 10, 20 years, it's so hard to say. I think it really depends on what nature has in store for us and if we're looking in the right places.
So Harry, you wear two hats, right? One is, you are, you're doing your research work, very deeply, at CERN, and then you also, through your books and other engagements, kind of educating public about science, physics, gets very complicated also very quickly. So maybe two-part question. One is for just a normal person, lay person who has interest in science. What can they do to learn so that you are, because this whole spectrum of things, things can get too simplistic, where you kind of lose the appreciation for what the real physics is, or gets so complicated that you feel like it's not for me. Someone who's enthusiastic about science, what is your advice to how do you go about learning about it? And just because we know a lot about our universe and things that this is kind of our collective heritage of how far science has come. So how can one go about developing deeper understanding?
Obviously buy my books and read them. I think it depends what you're after, really. And the way I came, my interest in science came from lots of different places. I think from my parents, and who encouraged me to ask questions and were always helpful in answering them, even if they didn't know. They would go and try and find out. Going to museums when I was a kid was a big part of it. So going up to the Natural History Museum in London and looking at like fossils of dinosaurs. A bit later on, reading popular science books, watching TV shows. I think you'll kind of find, as you explore, the kind of content that you want, and it depends on your level of interest, I think. And you have, things that are broader, that are for a wider audience. You have things that are more specific and more detailed. And I think one of the things about the, social media now is that there is this very rich collection of different communicators communicating at different levels. Some are sort of, higher level, some are, a deeper level. And it's really about, I think, about exploring and finding what works for you. And of course, I suppose the thing about science is you can appreciate it as a sort of spectator sport, I guess, where you have a kind of overview of what's going on, but maybe not a detailed understanding. But if, in physics particularly, if you really want to understand what's going on, the only way, unfortunately, to do that is to go and do a degree and, actually get to grips with the phenomena and the theories, because you can go a certain distance with analogy and, qualitative explanation. And that can give you certainly a feel for what's happening. And that's why I try and do with the book. My books, there's I think there's one equation in the first book, maybe two, equals mc squared, and then this equation that predicted antimatter, which I don't really try and explain. So you don't, but what I'm trying to do there is tell a story that gives you a sense of how all these ideas fit together. But if you really want to sort of really see the phenomena and understand them, unfortunately, the only way to do that is to go and enroll in a degree. But not everyone wants to do that. So I think it's really about, finding the sort of the niche that works for you. And in writing, you also have the spectrum of books, which go from the very broad and accessible. So things like Neil deGrasse Tyson's books, which are kind of aimed at a broad audience, or you have much more at the much more detailed end. You have things like Sean Carroll is writing writing a series of books at the moment. He's an American theoretical physicist, very well known in television and things. He's written lots of books, but he's got this series now which is called The Biggest Ideas in the Universe, and the idea there is trying to bridge this gap between popular science, which tends to avoid the sort of theory and the mathematics, with formal education. So he's kind of doing popular science but with mathematics and more of the detailed. And I think there is a big group of people who are not professional scientists, but who want a more in-depth understanding than you get from most popular accounts. So there is this wide. My book, I would say, probably sits somewhere in the middle of that. It's kind of more detailed than you get from Neil deGrasse Tyson, but not full of mathematics like Sean Carroll. So I think you have to sort of explore and find what works for you and suits your level of interest.
But it's incredible, that, we have this whole spectrum of things, from like something very, very simple to, I think you don't use equations, but I think you talk about physics in fairly detail. And then, I think, I was actually recently going to Sean Carroll's, 2 new books as well, The Biggest Ideas in the Universe. And it gets pretty hairy. You have to, at some point, you have to go from there to ChatGPT to explain this equation too.
I think there's this question about, what is science communication for? And my view generally, it's, when you read a popular science book, it's not the same as being educated, because the only way to learn something really is to do it, in the sense that, you don't go to university and learn just by listening to lectures. You have to go away and write essays or solve equations or do whatever. And it's the act that actually teaches you and you embeds that knowledge. Reading a book, I mean, I don't know about you, but I might read a non-fiction book and I might really enjoy it. But if you ask me 6 months later to summarize the salient points, I probably wouldn't be able to tell you very much anymore. But I think the role of science communication is not to necessarily get everyone to understand concept. It's more about exciting interest and developing enthusiasm and a general sense of understanding the world. And I think that's the more important role.
Right.
So I think when you read, when I finish a book, I don't expect to carry all that knowledge away with me, but it's given me a kind of broader overview of what's going on in science.
Yeah, look, at some point, everyone asks, these fundamental questions, who are we, where we come from, and so on. And, physics has come a long way to where we are able to at least see, where a bunch of stuff that we are made of, where it has come from, and so on. But I think the second part of my question is more about, which you kind of anticipated. So today, for someone, aspiring physics student, how should they think about, because physics also seems like in some ways very slow career. You have to invest decades of your life.
Yeah.
And I mean, there was a time, I think, I was reading, somewhere that after the World War II, there was this golden era of physics where pretty much everyone wanted to go into physics for 2 or 3 decades until, Cold War, kind of got over and, people moved on to other things. today somebody in their late teens, early 20s thinking about serious career in physics, how should think about, are we entering a next wave of, with all these anomalies and, unsolved answers that, we might be entering another golden period of physics, or you just have to be inherently very patient and, just do it for the love of doing science?
Yeah, I think the fact is that physics as a discipline is a very mature science. And it's the oldest, well, astronomy maybe you could argue, but astronomy and physics together, they're the oldest science, they're the best understood sciences. And when you have a science that is mature and well established, the fact is that the easy stuff has been done. The low-hanging fruit has been plucked. And what you're left with, we have these big fundamental challenges in physics. It's not that physics is wrapped up and done by any stretch. There's so much we don't understand. But these questions become more and more difficult to answer. It requires greater and greater technological innovation. It requires more and more difficult concepts. So as you go on in physics, you're kind of this curve of effort you have to climb gets steeper and steeper and steeper. And I think that's true in many disciplines. And it depends, I think, what kind of person you are and what kind of career you want to have. And I think, going into science in general is a risky business because you're exploring and you don't know what you're going to find and you don't know whether the thing you set off doing is going to bear fruit. And that's true in any area of science, I think. But, if you take particle physics in the 60s and 70s, it was a boom time in the sense there was lots of new things being discovered and new data and this new synthesis of all this information into a theoretical understanding that proved very successful. So it was an exciting time from that point of view. And it's certainly been less dramatic in some ways since then. But the fact is that if you want to make progress, you have to be dogged and determined. You've got to keep plugging away. And that's the only way we're going to really make progress in these much more mature areas of research. On the other hand, if you want to have a quick win, the thing to do is to identify an area of science where there's suddenly, usually the areas that accelerate very rapidly is when some new technique has been developed. And there you suddenly apply this new technique and you make lots of progress. A good example is the invention of the telescope in the early 16th century. I get my dates right. I think that's right. 17th century, maybe. Yeah, Galileo and all that jazz. But, once the telescope was pointed at the heavens, suddenly you see all these things you've never seen. You open up this new window on the universe, and you see all this stuff. You see craters on the moon, you see sunspots, you see the moons of Jupiter, and it transforms your understanding very, very quickly and rapidly. The same with spectroscopy, the same with colliders. So when you first have the first collider, that opens up this new view. And so what I suppose that the area that springs to mind at the moment is gravitational wave astronomy. So in the last 10 years, we've seen the first gravitational waves. This is a brand new way of looking at the universe. It's a bit like the invention of the telescope again. Yeah. And so we're seeing things that we could never see before and learning things we could never learn before. And the James Webb Space Telescope, another example, where this instrument that's allowing us to see back to times in the universe we've never been able to access until now. And that's when you make big strides, when you suddenly have this ability to see much further. And so, it ultimately depends on, what kind of stuff you're interested in and what kind of career you want to have. I think in high energy physics, in particle physics, the reality is probably it's going to be a slog. We are having to build these more and more ambitious and bigger machines that take longer and longer periods of time. Now, for some people, that might be, well, I don't want to spend my career doing that. And that's fair enough. But on the other hand, if we want to make progress in these fundamental questions, we have to keep pursuing this avenue. And I think it's a question of, in your career, hopefully you might have the big project that takes decades, but hopefully you also have some smaller things along the way that are maybe a bit more niche, but will keep you active and entertained while you're waiting for the mega collider to be built. Yeah,
that's something for, I think my youngsters to think about. But the good thing is, through the, work that you do, Harry, and through your books, etc., people can get, at least at a certain level, come up to speed very quickly and get a flavor for, where the science is, what the possibilities are, also what the challenges are. So I just want to thank you for, both taking the time to speak with me on this podcast, as well as, writing your book and all the work you are doing for public, education. And thanks so much, Harry, for great conversation and explaining, physics in a way at least I'm able to relate to, and hopefully a lot of our audience will be.
Well, thanks. It was really great talking to you.
Thank you. At SparX, we aim to bring to you stories of exponential impact. We share in-depth analysis of what goes behind success stories. If you find our conversations interesting, you can join us by subscribing to our YouTube channel. You can also listen to SparX on Spotify, Apple Podcast, or any other audio platform of your choice. If you have any suggestions on who we should invite or what topics we need to cover, just let us know in the comments. We are always listening, looking for ways to improve, and keep getting better as we go along.